way this goes is every single time I write it, you are more than welcome to comment and choose whichever method you would like to use. And we're going to start off easy in the very beginning. I have integral of x plus 4 cubed dx. Let me go ahead and just kind of write it down a little lower. I just realized my screen's a little too big. Oh yeah, here we go. Much, much better. All right, chat, let me know. Let me go ahead and write this down real quick. There we go. Now, there's a few ways that we can do this, but I want to get your thoughts. But if you see this, anyone in the comments, go ahead and let me know what you think the best method will be to use. Damn, integration exam in 14 hours. Good luck. I'm assuming the integrals here are not going to be as difficult as the one on your test, but I think it's always good practice to review these. Okay. This is a typical problem that a lot of people like to see, or when they do this, they're going to use U-substitution, but we're just going to take the scenic route for today. We're going to go ahead and expand this using Pascal's triangle. And if you remember Pascal's triangle, it looks a little bit like this. So then what this is going to turn to is x cubed plus 4x squared, 4 times 3 times x squared plus, this is going to be 16 times 3 times x plus, and then 64. And this becomes x cubed plus 12x squared plus 48x plus 64. I just wanted to expand it. I felt like it. And let's just go ahead and put a parenthesis here before I get yelled at by people. Hello from Chile. Hello. All right, guys, now we can go ahead and integrate this. And we're going to have x to the 4th over 4 plus 12x cubed over 3 plus 48x squared over 2 plus 64x. And don't forget your plus c. And also, don't write the integral once you're done. That's a common mistake that a lot of first-time calc students do. They'll continue writing the integral. We can get rid of it. So now we can go ahead and simplify, and we got x to the 4th plus, or x to the 4th over 4 plus 4x cubed plus 24x squared plus 64x plus c. That's it, chat. That's it. Yes, you can use U-substitution. There is absolutely nothing wrong with that, but I just wanted to expand it. All right, everyone, let's go ahead and try this next one. And again, as I write this down, I'm curious. Someone from Chile just tuned in. Where in the world are you tuning in? Where in the world are you holding your phone and watching someone solve integrals and discussing it with people all over the world? Man, I got that LaCroix, and it's making me burp every time. México, México. Yo soy de Chihuahua, o nací en Chihuahua, y me moví a los estados cuando tenía 7 años. Morocco, 1 a.m. Jeez, that's amazing. All right, guys. So as we solve this, people have a tendency to, yes, we're going to use U-substitution, but one of the U-substitutions that people do, and they should not do, in this case, is e to the t. We don't want that, okay? That's not going to be correct. The whole thing, our u value, is going to be e to the t squared plus 16. So when we take the integral du, now we have 2t e to the t squared t. And what I personally like to do is I like to move the 2t e to the t squared to the other side so that we have du over 2t e to the t squared equals dt. And the reason why I'm doing that is because when I start rewriting my integral, I have on the inside, it's just my u times, instead of dt, we're going to have du over 2t e to the t squared. And then I realized that I put my u, let me move this a little bit. I'll put that back in a second. But before we do that, we had t e to the t squared times, now we go ahead and write our du. Du over 2t e to the t squared, so that the t e to the t squared cancels out. And now we're left with the 2 in the denominator. And I personally like to just bring that outside. And now we have 1/2 integral of u du. Simple. U substitution is one of the best things that we can have, or one of the best methods that we that was introduced to us, so that we have in our arsenal. All right, now we go ahead and use the power rule to write u squared over 2, and we can simplify this as u squared over 4 plus c. But this isn't in terms of u, it was in terms of t. So we go ahead and substitute our original value for u, which was this one, back into our integral. And now our answer is going to be e to the t squared plus 16 squared over 4, and then plus. Nice. Okay, throw in an integral that you dare me to solve, and we might not be able to solve it at all, but I think it's always worth trying. Algeria, nice. Chile. Chile. All right, y'all. Let's try another one. Let's go ahead and increase the difficulty here. Let's go ahead and do integral of t. I don't like t personally. I hate when teachers give you problems involving t. Don't like it. All right, chat. There we go. Integral x secant squared x dx. Let me know in the comments what you think we should solve. All right, I'm writing down these integrals. Give me 1 second. Negative e, isn't that just the gamma function? Okay, I see that you gave me one of the integrals, and I'm gonna write it the way I would interpret it. But I could be wrong. Someone said trig sub. Trig sub. Trig sub. Interesting that we said trig sub. What would we use for trig sub if we did this? That's actually a good method, I think. But what would it be? Use a trig identity. Bro, what identity is this? Okay. Someone said integration by parts, and I think that's exactly what we're going to use. I'm going to go ahead and write integration by parts. We're going to solve it that way. Okay? And remember, integration by parts, we have uv minus v du, otherwise known as ultraviolet voodoo. And by the way, I do save the lives. However, they are on my reels for subscribers only. So if you fully support what I like to do, for a very, very, very cheap $1 a month, you can become a subscriber and see the replays here. I'm trying to add some value to people, to those that have subscribed already, and, you know, provide and give this replay for them. Anyway, we got to find our u, and our u value, I'm going to use x. That means that our du is going to be dx. And then our dv is going to be secant squared x. This one's easy, or pretty nice, because we can actually take the integral of that, and that's going to be tan x. All right, so now if we go ahead and use the ultraviolet voodoo, integration by parts, we have uv, so we have x tan x minus integral of v du. So we have tan x dx. That's not bad. Now, the only thing that we have to do is take the integral of tan x, and don't forget, we can go ahead and use an identity here and write it as sine x over cosine x dx. Because now we can go ahead and use u substitution. U is equal to cosine x. Let's actually use a different substitution, because we already used u. Let's go ahead and use w. W is equal to cosine x. dw is equal to negative sine x dx. And so now what we have is x tan x minus integral of sine x over u times dw over negative sine x dw. And luckily for us, the sine x's cancel out. The negative can come outside, so now we have a positive value. So we have x tan x minus or plus integral of 1 over u du. And that integral is very special. That's just natural log. So we have x tan x plus natural log of, I keep putting u, and that's not u, it's w. I'm so sorry, chat. 1 over w dw. So now we have natural log of absolute value of u plus c. All right, let me go ahead and create some space on the blackboard here. Let's go ahead and do this. Let's make this a tiny bit smaller and move this up on top. All right. Because now what we have, we just substitute the value of w back into our integral. So we have x tan x plus natural log of cosine of x plus c. That is the integral of x secant squared x. Integration by parts is amazing. Yes, math nerd, you're absolutely right. It was w. I think I changed. Oh, no. So someone caught my typo there. Someone was mentioning, hey, I'll highlight this in blue. That right there should not be a U. It should be a W. It's just because I was thinking about you. Thank you, math nerd. 3435. All right, y'all. Oh. All right, guys. Let's go ahead and try a different one. Let's go ahead and do integral of 6x minus 10 over x squared minus 4x plus 3x. And if you see this, oh, shoot. Sorry, guys, I'm just making sure. Let me know if the audio is still good. Double integral, bruh. Hey, we can try that one in a second. Let me write that one down. Anyway, but as you see this, go ahead and let me know in the comments what method we think we should use for this. I think I got that one. Someone said PFD, partial fraction decomposition. I 100% agree. Okay, so the best thing, whenever you have these a rational function, especially because we just have a linear function and then a quadratic on the bottom, we should go ahead and try to factor this out, because if we could, then beautiful, we can go ahead and use partial fraction decomposition. And it looks like we can. So this is going to be x minus 3 times x minus 1 dx. Okay, not bad. I like this one. And the idea for partial fraction decomposition is that this value should equal to the integral of the sum of these rational factors, okay? So we have these denominators, x minus 3 and x minus 1, so that means that we can go ahead and factor it out or break it apart and make it a sum of these rational expressions with these denominators. And the idea is that if you have a over x minus 3 plus b over x minus 1, think about what we have to do if you wanted to combine this. We would have to get common denominators. And for the sake of just everyone or people learning partial fraction decomposition for the first time, I'm just going to show you. I'm going to go ahead and introduce an x minus 1 to the first fraction and then an x minus 3 to the second one. Because the idea is that now we have a times x minus 1 plus b times x minus 3 over the common denominator. I keep putting minus or plus there. So x minus 3. And this should equal to 6x minus 10 over x minus 3 times x minus 1. And if you notice, the denominators are the same, which is great. And so now we can go ahead and say, all right, well, that means that the tops should equal to each other. And that's what we got to find. Okay, we got to find some values. Now, some people here like to use the cover-up method, and we totally can. But I'm going to go ahead and just solve it differently for today. All right, I'm going to go ahead and distribute the a to make it ax minus a. And then I'm going to go ahead and distribute the b to make it bx minus 3b is equal to 6x minus 10. And then I can go ahead and combine the x's that I have like this. A plus b, x, plus, and then the remaining values, which are your constants. Negative a plus 3b is equal to 6x minus 10. And so what that tells me is that the a plus b, which is a coefficient for the x, should equal to 6, and negative a plus 3b has to equal to negative 10. So then we have a plus b is equal to 6, and then negative a plus 3b is equal to negative 10. And we can go ahead and just use systems here. You're going to see that we have 4b is equal to negative 4, so b is equal to negative 1. And then at that point, a is just going to equal to... I just want to double check that. If you guys... So a is equal to 7. Let me know if I got that right. I could have totally gotten my math wrong. Okay, so double check, but I think that's going to be correct. It's funny because when I wrote my equation, that's not what I was expecting to get. So that's why I'm wondering if I wrote that wrong. I'm assuming that's going to be correct. Ah, there we go. There you go. There you go. Math nerd. Bro, I think this is the same math nerd that's on my TikTok because you always correct me. Thank you so much. So someone mentioned that, oh, right here. I'm going to highlight it in green. This is important when it comes to integrals. Any sort of typo is going to really cause a mess. So I'm going to highlight that in green. That should have been negative a minus 3b. Therefore, let me highlight this part here. Should have been negative a plus 3b, or minus 3b. That's the whole point. Negative a minus 3b. So then, things are going to change a little bit here. Because now what we're going to have is we're going to have negative 2b equals negative 4. So b is equal to just 2. And then a is equal to 4. Aha! Thank you, math nerd. Thank you. Okay, this is perfect. Now let's go ahead and create some space here on the blackboard and you can understand the partial fraction decomposition here. Because as I mentioned, this whole idea is that this integral can now be written as a sum of these rational expressions. Okay? And remember, we said that this integral 6x minus 10 over x minus 3 times x minus 1 is going to equal to the integral of a over x minus 3 dx plus integral of b over x minus 1 dx. We know our a value. Our a value is 4, and our b value is 2. So now we have integral 4 over x minus 3 dx plus integral of 2 over x minus 1. And I'm not going to show the work here, but if you do U-substitution, this is a very simple integral that just becomes 4 natural log of x minus 3 plus 2 natural log of absolute value x minus 1 plus c. And we're done. We're done, y'all. We are blessed that this was a partial fraction decomposition problem. Okay. Thank you. Hawkwing 1999. Yes, you're absolutely right. Thank you so much. You and Math Nerd are over here saving me. All right, that was a partial fraction decomposition. Now let's try something else. Let's talk about what happens when you don't have a partial fraction decomposition problem. And we'll see what we can do there. Okay. So let's go ahead and erase our work here. As I'm writing this, please feel free to just follow along. Follow me here on Instagram. Follow me on TikTok. Subscribe to my YouTube channel, even though I don't post much on there, but you know, it's always good. Okay, so how about we try this one? X plus 1 over x squared plus x minus 1. All right, chat. I'm counting on y'all. Let me know in the comments what you think we can do. And then I have a couple after this. We'll do one integral that someone recommended. It was a double integral. I think it's worth doing. That looked like fun. And once again, y'all, if I feel or if you see that I made mistakes, please feel free to call me out. I make so many typos, as does everyone. You know, I'm not perfect. All right, let me know what you guys think. Do I use partial fraction decomposition? Can we use PFD here, or should we use something else? I have an idea of what I want to use, but I'm curious as to what y'all think. Okay? Whichever method people comment first, that's the one I would do. I'm thinking of two different methods that we can do, but I'll do the first one that people comment. So let me know what you think in the comments, or let me know in the comments what you think we should do. And if you have to go, don't worry. Replays are on my reels for subscribers. Complete the square, then use substitution. That's what I'm going to do. All right. That wasn't my first choice, but I like it. Someone already introduced it, so why not complete the square? I hate completing the square, but it is so useful when it comes to integration. Okay? So let's go ahead and do the completing the square first, and then we'll talk about use substitution. So where problems like this, you look at it and you think to yourself, can I factor this? And no, you absolutely cannot. So we have to go to we have to use other resources. So let's go ahead and complete the square. And as much as I hate completing the square, you have to definitely know it. And remember completing the square, okay? We're going to take the b value. So in this case, that's our 1. That's the number in front of the x. We're going to divide it by 2 and then square it. And that's going to equal to 1/4. So now what we're going to do on the bottom, we're going to introduce the 1/4. But then we still need to have the same answer. We need to keep it consistent. So we're going to go ahead and introduce a negative 1/4. Because the idea is that these two cancel out and you still have the same answer. But the reason why we did that is because we're going to factor this quadratic there. This is going to easily become x plus 1/2 squared, and then minus, and this will be 5. Okay. Things are looking really, really good now. Because now we can go ahead and do use substitution. This one's really fun because we do u is equal to x plus 1/2, and then du is going to equal to dx. And it's not going to look as exciting yet. However, we have x plus 1 over, and then we have our u squared minus 5/4 times our du. Okay? But the issue here is that we still have a u and then we have x's. So what we have to go ahead and do is let's revisit our u value. And if we bring the 1/2 to the other side, we have u minus 1/2 is equal to x. So now we can go ahead and plug that value in for the x value in the integral. So what we really have is u minus 1/2 plus 1 over u squared minus 5/4 du. And this will become u plus 1/2 over u squared minus 5/4. Okay? Now, some people don't like the fraction. Some people get uncomfortable with that. That's okay. We can leave it like this. Or if you wanted to kind of get rid of all the fractions, you can go ahead and multiply everything by 4. So let's just go ahead and do that just to make it easier. I think it's more aesthetic. It's easier on the eyes. So let's go ahead and make this smaller, but we're not even done yet, but we have made our life a lot easier. You're going to see the light at the end of the tunnel here. So now what we have is we have integral of 4u plus 2 over 4u squared minus 5 du. Ugh. As ugly as I look, I still think this is good. Because now what we have, we can go ahead and separate this. We have two different integrals. 4u over 4u squared minus 5 du plus integral of 2 over 4u squared minus 5. All right, for the first one, we're going to go ahead and make our w equal to 4u squared minus 5. And then when we find our dw, we get 8u du. So then dw over 8u is equal to du. And now I'm just working on the first integral there, okay? So what we're going to have on the first one, we'll talk about the second one later, is we have 4u over our entire w times dw over 8u. And what's really nice is that the u's cancel out. 4 divided by 8 is 1/2, so we're going to go ahead and bring that on the outside. So then what we have, chat, is 1/2 integral of dw over w, which is just going to be 1/2 natural log of absolute value of w. Now, I'm not going to put the plus c because I'm still worried about the second one. So let's go ahead and make this a little smaller. If you guys have seen my lives, you notice that we do this all the time. We go smaller and smaller and smaller because our problems get more fun. That's what it is. All right, now we have 1/2 natural log of, the u value was 4u squared minus 5 plus integral of 2 over 4u squared minus 5 du. Okay, we still have that second integral. Super nasty. We got to do something about that, okay? This one's going to be a partial fraction. And it's actually one that we should have memorized, okay? But I'm going to work it out really quick. Or maybe I shouldn't. What do y'all think? Should I work it out or should I just give you guys the answer to this? In fact, I actually always forget it. So the way this, yeah, I'm just going to kind of show you guys how we're going to solve this one. Super annoying. Okay, but the way this works is when you have something like this, you might think it's going to be an arctan problem, but really this is going to be a partial fraction decomposition problem, and it's one that we should have memorized, but I'm just going to show you real quick. The idea is that this value can be rewritten as 2 over 4u squared minus 5, can be rewritten as a over 2u plus root 5 plus b over 2u minus root 5. So I just factored this one out. Okay, and so now what we have is we have 2 is equal to a times 2u minus root 5 plus b, and then 2u plus root 5. Bruh. Oh man, I guess I have to work it out. Yes, you're absolutely right. It is the difference of 2 squares. All right, very quickly, I just want to, for the sake of showing you guys, this is going to become 2au minus root 5a plus 2bu plus root 5b. Okay? And I'll put this up here, and then I'll make it smaller for us. So we have, actually, I'll make it smaller now. You see, a lot of the times, the integrals look very innocent, and then they just get crazy like this. All right, here we go. So as I mentioned, we have 2 is equal to, and then I'll pair all the u's together. So 2a plus 2b is equal to u, and then I'll pair the constants, so negative 5a or negative root 5a plus root 5b. And so what that means is that 2a plus 2b has to equal to 0, because that's the coefficient for u. We have no u on the left side, and then we have negative root 5a plus root 5b is equal to 2. Well, here we have to use systems, okay? And the idea, okay, or the way we're going to solve this is we're going to multiply everything by root 5 on the first one, and then we're going to multiply everything by 2 on the second one, so that we have 2 root 5a plus 2 root 5b is equal to 0. And then we have negative 2 root 5a plus 2 root 5b is equal to 4. And if you notice, using systems, the a's cancel out. So we're left with 4 root 5b is equal to 4. In other words, b is equal to 1 over root 5. Ooh. Okay. And then let's go ahead and use the 2a plus 2b is equal to 0. I meant to do that in red so that we can visualize that. Give me 1 second. So we're going to use this 2a. We're going to use a 2a plus 2b is equal to 0. Okay, so we have 2a plus 2. Instead of b, we have 1 over root 5 is equal to 0. So 2a plus 2 over root 5 is equal to 0, meaning that 2a is equal to negative 2 over root 5. And you probably guessed that a is equal to negative 1 over root 5. Y'all, we're doing this. Okay, we got to make this smaller. Don't forget, our u I just want, or u was equal to x plus 1/2. Because I'm definitely not going to be able to see it pretty soon. All right, guys, this is what we have so far. We have 1/2 natural log of 4u squared minus 5. That was the previous integral. And now we have plus integral of a over 2u plus root 5 plus b over 2u minus root 5, all du. But we know our values of a and b. So we have 1/2 natural log of 4u squared minus 5 plus integral of negative 1 over root 5 over 2u plus root 5 du plus our b value 1 over root 5 over 2u minus root 5 du. And these integrals are just going to be a simple log. I won't do the work for that one because I'm sure people are getting upset. Yes, we went from 30-something people to now half the amount in this room. If y'all are still here, I love you. All right, so now we have negative 1 over 2 root 5, natural log of 2u plus root 5, and then plus 1 over 2 root 5, natural log of 2u minus root 5 plus c. And I don't want to write this, but don't forget at the very end, our u was equal to x plus 1/2. So at the end, all you have to do is plug that back into our integral on top. Wow. Wow, what a ride. What a wild ride. Okay, I want to do this integral here. I don't even know if I can solve it, but someone mentioned in the comments that they wanted to do this. All right, this is a double integral. And here's my double integral. I believe it looks like this. I think that's the way it was written. X. Okay, so here we have a double integral, and the way we have to treat it is, I believe the way I wrote it, and I could be totally incorrect, but I'm going to work with the dx first, okay? So what we have is we have an integral of 1/3, integral of 0 to 2, and if I go ahead and distribute the e to the x plus y to both of these, now I'm going to have an equation of x e to the x plus y e to the x plus y dx dy. Oh, goodness. I have a feeling I already know what this value is going to be. Okay. Well, we have to integrate this. So we're going to start integrating the first one. Okay. The way we're going to solve this is doing integration by parts, where our u is equal to x, our du is equal to dx, and our dv is equal to e to the x plus y dx. This is still in terms of dx. And so our value, I believe, is just e to the x plus y. It's still the same value. So then using integration by parts, just for that first one, what I have kind of like highlighted there in yellow, what we have, actually I'll do this in green so people know and follow along what I'm doing. What we have is we have uv, so x e to the x plus y minus integral of v du, e to the x plus y. And that integral there is x e to the x plus y minus just e to the x plus y. That's the first one. Okay? So far what we have is we have integral 1/3, or 1 to 3, of x e to the x plus y minus e to the x plus y. But then we still need to take the integral of this part, what I'm highlighting in blue. And because y is just a constant there, that's the way we treat it when we do double integrals. This just becomes plus y e to the x plus y. And this whole thing is evaluated from 0 to 2 for our x values. So now we can go ahead and use the first fundamental theorem of calculus here. And we have 2 e to the 2 plus y minus e to the 2 plus y e to the 2 plus y minus, and then we're going to go ahead and plug in 0 for all the x values. So we have 0 e to the 0 plus y minus e to the 0 plus y plus y e to the 0 plus y. So I have our dy. Okay, let me go ahead and make this just a little smaller. Hope you're enjoying a double integral here. If you're taking Calc 1 or Calc 2, you will see this until Calc 3, typically in college. Oops, made this too big. That's what happens when we're working with this right here. Okay. So we have integral from 1 to 3 of 2 e to the 2 plus y minus e to the 2 plus y plus y 2 to the plus y e to the 2 plus y. Missing so many y's there. Okay. And now for this, the parentheses, the second part, the 0, e to the y, and the e to the y, those cancel out. Actually, no, they don't. The first one does. The first one just becomes 0. And then the other one is going to become plus e to the y minus y e to the y. And now the whole thing is in terms of dy. Okay. I have a feeling we can solve all of these. The only ones that we need to be careful with are these two. And that is the same idea as using integration by parts, sort of like the one on top. Okay, it kind of looks like this. So what we have now is we have 2 e to the 2 plus y minus e to the 2 plus y. And then this one right here, the one in blue, is going to become y e to the 2 plus y minus e to the 2 plus y. And then we have plus e to the y. And then we have minus y e to the y plus e to the y. And then we have the integral from 1 to 3. All right. Mather, what did I do? Hope I didn't scare you guys. I probably messed up. You probably caught the mistake. All right, at the very end, I'm not going to plug in the parameters 1 and 3. You guys can go ahead and plug it in, or if you wanted to do this on your own, you're more than welcome to. Not bad. Double integrals are sort of fun. Thank you. Thank you. Can you factorize the user properties? Oh, yeah, I think you absolutely can. So your question was whether in the very beginning we can go ahead and use e to the x plus y and do e to the x times e to the y. Absolutely. Because when you do that, and as you're doing double integrals, whether you're doing, let's just say this was in terms of x, then the e to the y becomes a constant. And if you're doing it in terms of y, then the e to the x becomes a constant. So yes, you absolutely can. It's funny, I didn't even notice that. I just saw the e to the x plus y, and I think I was just in the zone, and I just continued doing that. All right, y'all. Let's try another one. How about this one? Integral root x squared plus 2x plus 10. Okay, as y'all doing that, think about it. Let me know what you would do in the comments. Let me go ahead and turn on my light real quick, the light in my office. Yeah, I almost got rid of a term. I know, I was actually scared. I hate when I do these problems because I didn't prep for it and I can totally make a mistake. I get a little nervous, but I'm so used to it now. It happens. Thank you, Mathner. You're the best. Let me know, Chad, what we think we could do. Now we have a root, or we have a quadratic within a root. Okay? The very first thing that I would suggest when we have problems like this is go ahead and complete the square. Okay, so remember, completing the square, we have x squared plus 2x. So for completing the square, we take the b value, which is a coefficient in front of the x. We divide it by 2 and then square it. And in this case, that's just 1. So we go back to our quadratic, and now we introduce the 1. But because we introduced the 1, I need to make sure to subtract it. All right? And now we go ahead and factor out the quadratic x squared plus 2x plus 1. Because that's a really nice one. This just becomes x plus 1 squared. And then the remaining parts, 10 minus 1, is just going to become a positive 9. Ah, maybe from here we might be able to recognize it. Ooh, factor out a 9 and make a substitution. Someone said, I know exactly what you did with the factor out the 9. I necessarily don't like to do that because it'll still give you the same answer, but I know exactly where you're going. But you are on the right track. I mean, you are correct. Not even on the right track. You are correct. Okay. So someone said makes U substitution. We are going to do a U substitution, but let's make this even easier because otherwise we're going to have to do like double substitution. Okay. Someone said substitution by U. We are going to do a substitution, but we're not going to utilize the U right now, just so we don't have to do it twice. And someone said arctan, and it looks like that's the case. Okay. This is a trig sub. And the way I'm going to solve it is I always like to draw a triangle and imagine that we have our theta. And I'm going to make the opposite x plus 1. My adjacent is going to be 3. And if you use Pythagorean theorem, you will see that the hypotenuse is going to be x plus 1 squared plus 3 squared. So in this case, it's going to be 9. So now we can go ahead and set up some values here and make tan theta using SOHCAHTOA opposite over adjacent. So if I multiply the 3 to the other side, then we have 3 tan theta x plus 1. And now we can go ahead and derive or take the derivative of this and do 3 secant squared theta equals dx. Okay, that takes care of our dx. That's going to be the dx value. This is perfect. Now we just need to make sure we find an equation for the root. Now, if you look at the root, we can go ahead and do secant theta is equal to hypotenuse x plus 1 squared plus 9 over adjacent, so the 3. From here, we multiply the 3 to the other side. So we have 3 secant theta is equal to root x plus 1 squared plus 9. And now we can go ahead and rewrite our integral because we have the value for the root and then we have the value for the dx. So in here, remember, we have integral of that entire root is 3 secant theta. That's the entire root. So we have 3 secant theta times, oh no, I know exactly where we're headed here, dx. So it's 3 secant square theta d theta. I realized that when I took the derivative, I didn't put our d theta there, but hopefully we can see that. And so now what we can do is multiply the 3's together. That becomes a 9. Put it on the outside. And we have 3 secant cubed d theta. Oh boy. Yes, can you give me some integrals? Absolutely. Try to DM me or put them in one of the comments. Actually, DM me might be a little better, and I can make a video about it. And I can do it on the next live or just make a reel about that stuff. Oh, man. This is one integral that I tell people we should always know, and I always forget how to solve it. But we're going to work on it together, okay? So let's go ahead and make this a little smaller. How long have we been going for? We've been doing 45 minutes. Okay, not bad. All right, we got time. Let's go ahead and try to take the integral of this. So let's talk about how we're going to do or integrate secant 3 or secant cube theta. All right, we're going to go ahead and first rewrite it as 9 integral of secant theta times secant square theta d theta. And the reason why we're doing this is because we're going to use integration by parts. Okay? We're going to make u equal to secant theta. So that makes du equal to secant theta tan theta. And then we're going to make, or don't forget your d theta. And then we're going to make the dv equal to the secant squared theta d theta. And the reason why we chose that one is because you can easily take the integral of that, and that's just tan theta. So now what we have is we have 9, and then uv secant theta tan theta minus integral of v du. So that's secant theta tan theta times tan theta. And then don't forget the theta. So let's go ahead and do that. All right, and don't forget that so far this is supposed to be equal to 9 integral of secant cube theta d theta. Okay. Again, I did this for a reason, because now we can go ahead and do two things. I'm going to go ahead and distribute the 9 into both of these values. So now we have 9 secant theta tan theta minus 9 integral of secant theta tan theta, or tan square theta. No, I'm going to keep it as secant theta, tan theta. And then tan theta, d theta is equal to that entire integral. Okay, yes, someone said formula. Absolutely. Absolutely formula. Okay? And I believe I have it memorized, but God, I always forget it. And I hate it because every time I have to show how we got this answer, I always forget this last step. Okay. So this is supposed to equal to 9 secant cubed d theta. All right, y'all. Yeah, someone said use a formula. Absolutely. But again, there's some people that are going to say, how in the world did you get this? All right, y'all, here's what I'm going to do. In that integral, the only one that we really have to solve, I'm going to rewrite it as secant theta times tan squared theta. And this is still equal to 9 secant cubed theta. But remember, this right here, tan squared theta, okay? This is an identity. 1 plus tan squared is equal to secant squared. Therefore, tan squared is equal to secant squared minus 1. So we have 9 secant theta tan theta minus 9 integral of secant theta parentheses secant squared theta minus 1 d theta, and that's 9 integral of secant cubed theta d theta. Almost done, guys. Because now what we have is we have 9 secant theta tan theta minus 9. And check this out. If I distribute the secant into both these, I get minus 9 secant cubed theta plus 9 integral of just secant theta. And then the whole thing has d theta, so both of them have theta. Yeah, I keep making this equal to the original integral. You're going to see why in a second. And then we're going to be done. All right? And after this, we can finish our session. We can finish the live, and we could go about our ways. Some people are tuning in at 1 in the morning. Some people are tuning in the afternoon. I thank you for that. Y'all are real ones. Okay. So here's what we have now. We have 9 secant theta tan theta minus 9 integral of secant cube theta d theta plus 9 integral of secant theta d theta is equal to 9 secant cubed theta d theta. I'm going to do two things. One, let's go ahead and add this 9 secant cubed theta to the other side. That's real nice. And then at the same time, this integral secant theta, I'm not going to get into the proof, but that is an integral that we should know. So now we have 9 secant theta tan theta plus 9 natural log of secant theta plus tan theta is equal to 18 integral of secant cube theta d theta. And we're going to divide everything by 18. All right. Almost done, y'all. Almost done. I didn't realize that I needed even more room on here. Let's go ahead and make this smaller. Not small enough. Let's shrink this bad boy. There you go. All right, y'all. When we divide the 18 to the other side, luckily for us, if you can keep track of those 9s, when we divide the 18 to the other side, those are just going to become 1/2. So we have 1/2 secant theta tan theta plus 1/2 natural log of secant theta plus tan theta is equal to integral of secant cube theta d theta. And I know someone said use the formula. Absolutely, but I wanted to show you how we get integral of secant cube theta. All right, so this is the integral. Now remember, at the very end, secant cube theta was... Actually, this is our integral here that we were trying to solve. Now we just go back to the triangle that we had a long time ago. And remember, we this x plus 1, this was a 3, and then the hypotenuse was x plus 1 squared plus 9. So therefore, at the end, we just go ahead and substitute the values of secant and tan. So secant theta is going to equal to root x plus 1 squared plus 9 over 3. And then tan theta is just going to equal to x plus 1 over 3. I put x plus 3, my bad. Okay, and you plug those into your integral and you're done. That is your solution. Why don't I divide by 2 as it's equal to the original integral? Yeah, I wanted to show the work there. Okay. This is something that I wouldn't recommend you doing on a test. The integral of secant cubed and the integral of secant should be somewhat memorized. This is something that you should definitely. And someone said, "Oh shoot, you're absolutely right." And someone said, math, bro, math nerd, you're the best." So if you look at this solution, I'll put this in red. Our original, what we were trying to solve was 9 integral of secant cube theta. So at the end, I didn't even have to like divide by 18, or I didn't have to actually, I don't know what I did there. At the end, what I should have done is we need to multiply everything by 9, because what we're looking for is 9 integral secant cube theta. So really at the end, our answer is 9/2 secant theta tan theta plus 9/2 natural log secant theta plus tan theta. Yo, how many typos did I make today? The book of derivatives is honestly for any calculus student that wanted to review 1,000 derivatives. The book of antiderivatives, let me tell you, hold off on that. Okay? It has 100 what I thought was challenging antiderivatives, and it's not the best. All right? But I am working on a book of 1,000 integrals that's going to have a plethora of different integrals, different methods, and I'm going to walk you through them, and then hopefully you'll have 600-700 integrals to do on your own using all the methods that I have taught you in the book. So hold off on that one. But if you wanted to go and purchase the calculus bundle that has limits, derivatives, the integral book, and then I believe it has another book on there. So 4 books. Oh, area under the curve. And that's, I think, worth your value. And if you purchase that, just let me know when the integral book comes out, and I'll send you a free copy. That was it, guys. That was it. I'm going to head out. If you want to watch the replay, it's going to be on my reels for subscribers. I wanted to add that value to them because they are the ones that are supporting me through a subscription. But if you want to find other ways to support, you can always just like this live. You can follow me on Instagram, follow me on TikTok, and just continue discussing. Go in the comments and, go over some of those problems and put your input on that. And I appreciate you all, every single one of you that's on this live, every single one of you that subscribes, that follows. Thank you so much. This is my full-time job, and it's really, really fun to be online and talk integrals or just math in general with you nerds. I appreciate y'all. But anyway, I'm going to head out. I hope you guys have a fantastic rest of the week. If you guys are on TikTok, I will see you on Thursday around the same time, where we will do either more integrals or just some crazy math that some ideas that I might have, but I'll see you then. But if you're just going to watch me on Instagram, catch the reels for subscribers, or I'll see you next Tuesday. All right, y'all. Take it easy. Love you. Peace.